You've learned elimination on square matrices. But what happens when a 0 appears in the pivot position and there's no row below to swap with? Most students freeze here, and they think elimination has failed. It hasn't. And that 0 tells you something fundamental about the matrix structure. Learning to read that signal is the key to understanding the null space. Let's see this in action with a concrete example. Here's our matrix A, a 3x4 matrix. Row 1 is 1, 2, 2, 2. Row 2 is 2, 4, 6, 8. Row 3 is 3, 6, 8, 10. We want to solve AX equals 0, that is, find every vector x in the null space. The null space means all solutions to AX equals 0. Before we compute, notice two things. Column 2 is exactly 2 times column 1. Check it. Column 1 is 1, 2, 3, and column 2 is 2, 4, 6. Also, row 3 equals row 1 plus row 2. 1 plus 2 is 3, 2 plus 4 is 6, 2 plus 6 is 8, and 2 plus 8 is 10. The matrix has built-in dependencies. Watch whether elimination discovers them on its own. The first pivot is 1 in position row 1, column 1. We now eliminate below it. For row 2, we compute R2 minus 2 times R1. Take the row 2, 4, 6, 8, and subtract 2 times 1, 2, 2, 2, which gives 2, 4, 4, 4. Subtracting, we get 0, 0, 2, 4. Next, for row 3, we compute R3 minus 3 times R1. Take row 3, 6, 8, 10, and subtract 3 times 1, 2, 2, 2, which is 3, 6, 6, 6. That gives 0, 0, 2, 4. Our intermediate matrix is now row 1 unchanged at 1, 2, 2, 2. Row 2 is 0, 0, 2, 4. And row 3 is 0, 0, 2, 4. Now look at position row 2, column 2. It's 0. This means column 2 does not have a pivot, and we'll need to look further to the right for the next pivot. Now we need a pivot in position row 2, column 2, but the entry is 0. Right? In a square matrix, we try swapping with a row below, but look at row 3. It also has a 0 in column 2. Every entry below the pivot position is 0, so no row swap can help us. Right? Here's the critical insight. Elimination has not failed. We simply skip column 2 and move on to column 3. At position row 2, column 3, we find the value 2. That becomes our second pivot. Because column 2 has no pivot, it is called a dependent column, sometimes also called a free column. Now we finish elimination. Row 3 minus row 2, we take 0, 0, 2, 4, and subtract 0, 0, 2, 4. 0 minus 0 is 0. 0 minus 0 is 0. 2 minus 2 is 0. 4 minus 4 is 0. That gives us 0, 0, 0, 0, a completely 0 row. The echelon form U is now complete. Row 1, 1, 2, 2, 2. Row 2, 0, 0, 2, 4. Row 3, 0, 0, 0, 0. Echelon form means we have a staircase pattern of pivots where each pivot sits to the right of the one above it. Our pivots are the one in position row 1, column 1, and the 2 in position row 2, column 3. That 0 row in row 3 confirms that row 3 of the original matrix was dependent on the other rows. Elimination discovered both dependencies automatically. Column 2 is a free column, and row 3 was a dependent row. Now we read the structural story from U. Count the pivots. There are 2. This count has a special name, the rank. The rank equals the number of pivots. For our matrix, the rank of A equals 2. This single number is the most important structural fact about any matrix. A 3x4 matrix could have rank at most 3 since the maximum rank equals the minimum of the number of rows and columns, which is the minimum of 3 and 4, giving 3, that's 1 pivot per row at most. Ours has rank 2, meaning 1 row was redundant. It contributed no new information. The rank determines everything that follows. Rank partitions the columns into 2 types. Columns containing pivots are called pivot columns, and columns without pivots are called free columns. In our echelon form, U, column 1 has the first pivot and column 3 has the second pivot. So columns 1 and 3 are pivot columns. Columns 2 and 4 have no pivots, so they are free columns. Each column corresponds to a variable. x1 and x3 are pivot variables. x2 and x4 are free variables. The general formula is for an n by n matrix of rank R, there are R pivot variables and n minus R free variables. In our case, n minus R equals 4 minus 2, which gives 2 free variables. Free variables can be set to any value we like. The pivot variables are then determined by back substitution. And this is exactly why the null space contains more than just the zero vector. The free variables generate an entire family of solutions. One important subtlety. Elimination preserves the null space, but it changes the column space. The columns of U are not the same as the columns of A. So for null space questions, you can use U freely. AX equals 0 and UX equals 0 have identical solution sets. But for column space questions, you must go back to the original matrix A. Now let's connect this to what we noticed at the start. Column 2 of A was exactly 2 times column 1. Elimination flagged column 2 as a free column. There was no pivot there. Column 4 depends on columns 1 and 3. Specifically, column 4 equals negative 2 times column 1 plus 2 times column 3. Elimination flagged column 4 as free too. The pivot columns 1 and 3, are the independent columns of A. The free columns 2 and 4, are the dependent columns. Elimination doesn't just solve systems. It classifies every column as either independent or dependent. The dependencies we spotted by eye, elimination discovered through pure computation. Let's step back and see the big picture. On the left, consider a square invertible matrix where the rank equals n. In a square invertible matrix, every column is a pivot column. The rank equals n, which means there are 0 free variables. The null space contains only the 0 vector. The system AX equals 0 has only the unique trivial solution. Now on the right, the moment a matrix becomes rectangular or singular, the story changes completely. Free variables appear, and the null space becomes non-trivial. Our 3x4 matrix U with rank 2 has 2 free variables in columns 2 and 4. Those free variables parameterize the null space, which has dimension n minus r equals 4 minus 2, which equals 2. So the null space is a two-dimensional subspace, a whole plane of solutions. Now, the key takeaway is that rank is the dividing line between trivial and non-trivial null spaces. Rank determines the entire story. The next time elimination produces a 0 where you expected a pivot, don't panic. Skip the column, keep going, and read the story that elimination is telling you. Here are the 3 key takeaways. First, a 0 pivot means skip the column, don't stop. Second, the rank R equals the number of pivots, and this gives you R pivot variables and n minus R free variables. Third, pivot columns correspond to independent columns, while free columns correspond to dependent columns. Let's see this one final time with our running example, the original matrix A, which was 1, 2, 2, 2, 2, 4, 6, 8, 3, 6, 8, 10, reduces to the echelon form U, which is 1, 2, 2, 2, 0, 0, 2, 4, 0, 0, 0, 0. The final stamp, rank equals 2, 2 pivots, 2 pivot variables, 2 free variables, and a two-dimensional null space. Rank pivots and free variables are not just computational artifacts. They are the structural skeleton of the matrix.